Hello students, welcome to EPG Pathshala. I am Dr. Nidhi Handa from Gurukul Kangli Vishwavidyalaya, Haridwar. Today we are going to talk on module Discrete Probability Distribution, Binomial Distribution under the paper Quantitative Techniques for Management Decisions. After completing this module, you should be able to understand introduction, binomial probability distribution, binomial experiments, condition of binomial experiment, then some related problems are also discussed, and in the end summary. First of all, introduction. The binomial probability distribution. The binomial probability distribution is one of the most widely used discrete probability distribution. It is applied to find the probability that an outcome will occur x times in n performances of an experiment. For example, given the probability is 0.5 that a mobile manufactured at a firm is defective, we may be interested in finding the probability that in a random sample of 3 mobiles manufactured at this firm, exactly one will be defective. As a second example, we may be interested in finding the probability that a baseball player with a batting average of 0.250 will have no hits in 10 trips to the plate. To apply the binomial probability distribution, the random variable x must be discrete dichotomous random variable. In other words, the variable must be a discrete random variable. That is why dichotomous word is used. And each repetition of the experiment must result in one of the two possible outcomes. The binomial distribution is applied to experiments that satisfy the 4 conditions of a binomial experiment. These conditions are described here. Each repetition of a binomial experiment is called trial or a Bernoulli trial due to Jacob-Bernoulli. For example, if an experiment is defined as one toss of a coin and this experiment is repeated 10 times, then each repetition is called a trial. Consequently, there are 10 total trials for this experiment. So there are some conditions for the experiment to be binomial. The binomial experiment, an experiment that satisfies the 4 conditions is called a binomial experiment. Number 1, there are n identical trials. In other words, the given experiment is repeated n times. All these repetitions are performed under identical conditions. Each trial has 2 and only 2 outcomes. This is second point. These outcomes are usually called a success and a failure. Each trial has 2 outcomes. Number 3, the probability of success is denoted by P and that of failure by Q. And P plus Q is equal 1. The probability P and Q remain constant for each trial. Number 4, the trials are independent. In other words, the outcome of one trial does not affect the outcome of another trial. Different conditions of a binomial experiment. If we see that there are n identical trials, each trial has only 2 possible outcomes, the probability of 2 outcomes remain constant and the trials are independent. Note that one of the 2 outcomes of a trial is called success and the other is failure. Similarly, a failure does not necessarily refer to an unfavorable or undesirable outcome. Success and failure are simply names used to denote the 2 possible outcomes of a trial. The outcome to which the question refers is usually called a success. The outcome to which it does not refer, it is called a failure. Example, 5% of all mobiles manufactured by a large electronics company are defective. 3 mobiles are randomly selected from the production line of this company. The selected mobiles are inspected to determine if each of them is defective or good. Is this experiment a binomial experiment? Now, how will we do this example? Number 1, this example consists of 3 identical trials. A trial represents the selection of a mobile. Number 2, each trial has 2 outcomes. A mobile is defective or a mobile is good. Let a defective mobile be called a success and a good mobile be called a failure. Number 3 point, 5% of all mobiles are defective, so the probability P, that is defective mobile, is 0.05. As a result, the probability Q that a mobile is good is 0.95 because we will subtract 0.05 from 1. These two probabilities add up to 1. Number 4, in each trial mobile is independent. In other words, if one mobile is defective, it does not affect the outcome of another mobile being defective or good. This is so because the size of population is very large as compared to the sample size. Since all 4 conditions of binomial experiment are satisfied, this is an example of binomial experiment. The binomial probability distribution and binomial formula. The random variable x that represents the number of successes in n trials for a binomial experiment is called a binomial random variable. The probability distribution of x in such experiments is called binomial probability distribution or simply binomial distribution. Thus, the binomial probability distribution is applied to find the probability of x successes in n trials for a binomial experiment. To solve binomial problem, we determine the value of n, x, n minus x, p and q. Then substitute these values in the binomial formula. To find the value of NCR, we can use either the combination formula or the table of combinations from the table. To find the probability of x successes in n trials for a binomial experiment, the only values needed are those of n and p. This is very important point. That is why these are called parameters of the binomial probability distribution. Binomial distribution is known by the two parameters, that is n and p. So, the value of q is obtained by subtracting the value of p from 1.0, thus q is equal 1 minus p. Binomial distribution, if we see how it occurs, repeated independent trials with 2 outcomes. Consider an experiment of repeated trials in which each trial has only 2 possible outcomes. Such a situation always arises when we deal with testing of items. Each trial indicates whether the item is defective or non-defective. Let a trial be repeated so that we have a series. If n trials are there, let P be the probability of success and Q be the probability of failure in each Bernoulli trial, so that P plus Q is equal 1. Bernoulli trials is named after Swiss mathematician Jacob Bernoulli, and it is required to find the probability of R successes in n trials. If S denote the successes and F denote the failure, then probability of R successes and n minus R failures can be given in the following way. Suppose success, then failure. Suppose we toss a coin and success first, we get success, then failure, then success. In the fourth trial again success, in next trial failure and success, and so on. Then the probabilities allotted to this are P, Q, P, P, Q, P, and so on. Let this be P raised to power R, because R successes, so P into P, R times P raised to power R, it comes out to be P raised to power R, and n minus R times failures means Q raised to power n minus R, as a number P is equal to the number of successes, and so on. In order to find the required probability, we have to count all different orders in which R successes and n minus R failures can occur. This is in fact all possible arrangements of n letters, which are S and success and n minus R are failure, F, and is equal to NCR divided by NCR, which is written as n factorial upon R factorial into n minus R factorial. So by addition theorem, the probability of getting R successes in a trial is NCR into PR into Q raised to power n minus R. We notice that probabilities of 0 trial is assigned Qn, probability of 1 trial is assigned Nc1, P raised to power 1, Q raised to power n minus 1, and so on, which are successive terms of binomial expansion also of the expression Q plus P raised to power n. Hence, the above probability distribution is known as binomial distribution. That is why it is known as binomial distribution after Bernoulli's name. It can be noted that sum of all probabilities is 1, because Q raised to power n, Nc1, P raised to power 1, Q raised to power n minus 1 plus dash up to Pn. This reduces to P plus Q raised to power n. And since P plus Q is always equal to 1, so 1 raised to power n is 1. The probability that a particular type of component will survive a given shock test is 2 by 3. Find the probability that 2 of the next 5 components tested will survive. Let the shock test of the component be regarded as a trial and its survival as a success. If P denotes the probability of success, Q that of failure in a single trial, then number of tests n is equal 5, P is given, Q is given, required probability that 2 successes is P and R. R is 2 successes, number of success. So NCR is P raised to power R, Q raised to power R. After solving, you will get the answer. The next example, the probability that a patient will survive from a delicate heart operation is 60. What is the probability that exactly 5 of the next 7 patients having this operation will survive? Let the heart operation of the patient be regarded as a trial and his survival as the success. If n denotes the number of trials, P the probability of success, and Q that of the failure in a single trial, then n is equal 7 as given. P probability is 0.9, that is 90%, and Q is equal 1 minus P, that is 10%. Required probability is equal probability that exactly 5 out of 7. So NCR 7 CR P raised to power R Q raised to power n minus R, that is 7 C5 0.9 raised to power 5 and 0.1 raised to power 2, and solve the question and have the answer. Next example, if 10% of the components produced by a machine are defective, determine the probability that out of 5 components selected at random, first is none, second is 1, and at the most one component will be defective. So let we see how we'll do this question. Since 10% of the components, that means probability is given. 5 components selected at random, that is n is also given. So let n denotes the number of trials, p probability of success, and q that of failure. So here n is equal 5, p is equal 10%. 10% means 0.1 and q is equal 0.9. Probability that no success, 0. So this will be equal to q raised to power n, and probability of one success is NCR, where r is 1. That means 5C1, p raised to power r, that is 0.1 raised to power 1, 0.9 raised to power 4. And how to calculate the probability of at the most one success is, what we have to do, we will solve probability that no success is got plus probability that one success is got, and then we sum up both probabilities and have the answer. The incidence of an occupational disease in an industry is that the workers have 20% chance of suffering from it. Find the probability that out of 6 workers selected at random, 4 will catch the disease. Numbers 2, at least 4 will catch the disease. Let the selection of a worker be regarded as a trial and suffering from the disease as success. If n denotes the number of trials and p the probability of success, q that of the failure, then n as given is equal 6, p is 20%, so 20 upon 100, q is 1 minus p, that is 4 by 5. So probability that there are 4 successes, NCR, that is 6C4, p raised to power r and q raised to power n minus r. Solve accordingly, put the values of n, r and p and q respectively. Second is probability that at least 4 successes. That means at least imply that probability of 4 successes, probability of more than this, probability of 5 successes plus 6 successes. Only 6 trials are done, so up to 6 successes. We will calculate all the 3 probabilities, then we will take sum of these 3. The required probability will be probability of at least 4 successes. The probability that a bomb dropped from a plane will strike the target is 1 by 5. If 6 bombs are dropped, find the probability that exactly 2 will strike the target. Number 2, at least 2 will strike the target. Let the dropping of a bomb be regarded as a trial and striking the target as the success. So n is equal 6 here, p is equal 1 by 5, and calculate q of subtracting from 1 the p probability. Probability of 2 successes, NCR, p raised to power r, q raised to power n minus r, by following this formula, and value of r is 2. Probability of at least 2 successes is, find the probability of 0 success, probability of 1 success, and then subtract it from 1. This is also another way of finding out at least successes. Then next, computing of central tendency and dispersion for the binomial distribution. Mu, which is a donation for mean. Mean is NP, binomial distribution. Standard deviation, which is sigma. For binomial distributions, standard deviation is NPQ under root, or variance is NPQ for binomial distribution. Example, modern filling machines fill toothpaste to the desired level of 80% of the time. What is the probability that exactly half the tubes in a carton selected at random will be filled? Total tubes are 6, so n is equal 6. Probability is 80% of for success, p is equal 0.8, and q is calculated from 1 minus 0.8, that is 0.2. Using binomial formula, probability of R successes and trials NCR P raised to power R or Q raised to power X minus R. So using this formula, we will calculate. Next question, a packaging machine produces 20% defective packages. If we take a random sample of 10 packets, find the mean and standard deviation. So here X follows binomial distribution with N and P. N is 10 here, probability is 0.2. So use the formula of mean and standard deviation, that is into P and NPQ under the root for standard deviation. Next example, if 5% of the items produced turn out to be defective, then find out the probability that out of 20 items selected at random, then are exactly 3 defectives, second at least 2 defectives, third exactly 4 defectives, and the last find mean and variance. So probability is 5% of the items. An item produced can either be defective or non-defective. Thus there are only 2 outcomes. The probability P of a defective item being produced is 5%, that is 0.05, and it remains constant. Further, the trials are independent, thus inspecting a small sample of 20 can be conceived as a repetition of Bernoulli trials. Therefore, parameters of binomial distribution are as such: n is 20, p is equal 0.05, that is B binomial distribution with parameter and p. Number 1, probability if x takes exactly 3, that is exactly 3 defective items. So NCR P raised to power R Q raised to power N minus R. Second, probability X takes greater than equal to 2, that is at least 2 defective items, 2 or that means 2 or more than that. So the probability of 2 defectives plus probability of 3 defectives and so on, probability of all defectives. That means 1 minus, to cover probability x is less than 1 and x is 0. So 1 minus probability of no defective items minus probability of 1 defective items. This is the required probability for P of x greater than equal to 2. Third is probability x takes 4, that is exactly 4 defective items. For this again follow the formula NCR P raised to power R Q raised to power N minus R. At the end, mean is n into p and variance is npq. We know the value of p and hence variance. So probability of success is, for any number of trials, binomial probability distribution is symmetric if p is equal 0.5. The binomial probability distribution is skewed to the right if p is less than 0.5. The binomial probability distribution is skewed to the left if p is greater than 0.5. These are 3 important points in binomial distribution. So students, let us now summarize what we have learned in this module. Here, out of 2 special probability distributions, binomial distribution and Poisson distribution, for a discrete random variable, because both of them come under discrete random variable. The binomial distribution is developed here since decisions are made under uncertain conditions. Therefore, here we explain if outcomes and their probabilities for a statistical experiment are known, we can find out what will happen on the average if that experiment is performed many times. For a lottery example, we can find out what a lottery player can expect to win or lose on an average if he continues playing his lottery again and again. So the concept of factorial and combination are also discussed in this module. Thank you.